Alright, let's continue on the notes page. So here's just a little bit of a smaller version of the picture we're just looking at, our Bohr model diagram of the atom. And now we're going to be looking at the subatomic particles and different properties of them, where they're located in the atom, and so on and so forth. So let's go ahead and fill in the names of these particles: proton, neutron, electron, and the spaces here under subatomic particle. Subatomic just meaning, of course, within the atom. And let's start off with mass. Now, in class I would ask you if anyone happens to know the mass of any of these particles off the top of their head in kilograms, and that's usually not information most of you do have on the top of the head, but of course I do. It's my job to know these things. So we're going to fill in the mass of a proton as 1.67 times 10 to the negative 27th. Yeah, you probably were not going to guess that. And then I would ask if anyone happens to know the mass of a neutron, and some students may have some knowledge of this, but I'm just going to go right ahead and tell you it's 1.67 times 10 to the negative 27th. And then I would ask the mass of an electron, and some students think they're all smart and they say, oh, it's 1.67 times 10 to the negative 27th. No, you're wrong. It's 9.11 times 10 to the negative 31st. Of course, right? Okay, you probably weren't going to guess any of those. But then I would start to ask, I was to see if there's any patterns. And first of all, we notice that the mass of the proton and neutron are the same. Now, it turns out that's not exactly right. If you go to a fourth sig fig, this is 1.675 for the proton. 1.675 for the proton, 1.673 for the neutron. They're off by just a little bit. I just got those reversed. But the point is that to 3 sig figs, they both round to about 1.67. And so it's some weird cosmic, just coincidence that the mass of a proton and the mass of a neutron are almost the same. They're off by just a tiny bit, and no one really knows why. But for some reason, they're almost the exact same mass. But the electron is completely different. But then I would ask, in general, how would you describe these masses looking at these exponents? And hopefully you recognize that they're really small. Right? 10 to the negative 27th, that's a billionth of a billionth of a billionth of a kilogram. Let's see if we can visualize that. Okay, so here's a kilogram. This is one of the standard mass sets that you often see we use on the lab stations. I usually have demonstrations of little hooks on the top. Just to put this in perspective, here it is next to a triple beam balance, a device we're pretty used to, right? So looking at one of these, this is 1,000 grams. This is 1 kilogram. So imagine you took this and split it apart into a billion pieces. Okay, try to visualize that. All right, you got that? Now take one of those pieces and imagine splitting it apart into a billion pieces. Okay? You got that? Now, take one of those and imagine splitting it into a billion pieces. Right? Can you visualize that? No, you can't, right? But what you're trying to visualize right now is the amount of matter that one of these protons or neutrons takes up, because it is a billionth of a billionth of a billionth of a kilogram. That means that inside this object right here are a billion, billion, billion things, and that's just the protons. And there's also the neutrons, and then there's the electrons also, right? And that's just 1 kilogram. You are 50 or 60 or 70 kilograms. So there are more tiny little things inside of you than you can even comprehend. That's crazy, right? That's the sort of stuff that keeps you awake at night, wondering, oh my gosh, what if my protons don't know what to do? Don't worry, your protons know what to do, the electrons know what to do, they follow rules, they're going to do exactly what they're supposed to do. It's fine, right? But that does sort of mess with your head. It really changes your perspective on things. That we're talking about ridiculously tiny objects, right? So the atom, that's something we can't even see. It's even difficult to visualize what that is, right? And these protons and neutrons are even smaller than that. And then the electron, that's 10 to the negative 31st. That's smaller, right? It's even smaller than what you're trying to visualize for the proton or neutron. That's kind of crazy. So our perspective is completely changed here. We're thinking about just the most tiny of tiny objects, things that are just difficult to even comprehend. And yet, these are the fundamental building blocks of matter. All right, and now we're talking about the idea of charge. So remember, the charge is this quality that some objects have it, some don't. Like the proton, neutron, the proton, electron, they have charge, which means they can interact with each other in some way. The neutron, remember, being neutral, doesn't, which means it just can't interact in the way that the other ones do. And we mentioned that the symbol for charge is lowercase q. This capital C, that's the unit of charge. That's named after Charles Coulomb. It's C-O-U-L-O-M-B. So one capital C is 1 Coulomb. Now, he was French, so it's probably like Coulomb or something like that. My French is not very good, so we're just going to say Coulomb. All right, then in class I would ask, does anyone happen to know the charge on a proton? Now, often some hands go up and students say, well, it's positive. Well, that's great, but that's not in our standard units here. So yes, we know protons are positive, but in coulombs, the value is positive 1.60 times 10 to the negative 19th. Okay, and then I'd ask, well, what's the charge on a neutron? And hopefully you know this one, it's 0, right? Because no matter what, it's a neutron. It's neutral. It doesn't have an electric charge. And then what about the charge on an electron? And then usually some brave hands go up and people say, well, it's this. It's negative 1.60 times 10 to the 19th. And that is correct. These are in coulombs here, right? And so it turns out that not even off by just a little bit, these values are exactly the same. The amount of charge on a proton is exactly the amount of charge on an electron to every level of precision we could possibly find. They're exactly the same amount of charge, but there are two different types of charge, and so we decided to use the words positive and negative to indicate that. Now, these words really just mean opposites. They could have been any two words that meant opposite. It could have been up and down, left and right, good and evil, but to make it more mathematical, whoever it was decided that it would be positive and negative, and so that's the way we describe the two different types of charge. Positive and negative. Protons are positive, electrons are negative, but the amount of charge, whatever this idea of charge is, on the proton is exactly the amount of charge on the electron, which is why we had 3 protons in the nucleus of this lithium. We needed 3 electrons to balance it out, so that all the positives balance out all the negatives, and this is overall a neutral electrical object. Let's go on to the location of the atom. So as we can see from our diagram here, the protons, of course, are located inside the nucleus. They are stuck inside. They are not moving around. And the neutrons are also located inside the nucleus. In fact, there are what we call strong nuclear forces binding the protons and neutrons together, almost like glue. And they are stuck. They do not move around. Maybe they vibrate a little bit, but they certainly don't move. What does move are the electrons. So where are they? They're in motion outside the nucleus. In fact, this picture is not even close to being to scale. These electrons not only in motion, but they're actually very, very far away from the nucleus on the atomic scale. We just draw it like this so we can visualize it, but it's not even close to being to scale as what we'd actually see if we were this close to an atom. And so they're very far away, they're outside the nucleus, and they're in constant motion, remember. That's why we draw the arrows there to indicate they're in motion, sort of circling, orbiting the nucleus. Okay, so as you can see on your notes page, it is now time for fun with balloons. And so we're going to shift videos here so you can watch a demonstration that I did, because I did happen to have some balloons at home and some string, and I employed the use of 2 of my daughters. You'll see my daughter, our youngest daughter, Samantha, helping me out, and my middle daughter, Rebecca, is taking the video. So I wanted to give them some credit, a little shout out as you watch that video.